Miss Jody here with another video for chemistry that meets usually on Mondays from 1 to 3:30. So I'm a little behind this week with videos because I had some stuff that had to be done at the center, Turtle Pond, and we've had a few things going on here. Plus I've had some emails and other projects that had to get done. So I'm a little behind, but we're still cruising along here. We are now moving in, excuse me, to chapter 14, and that is on the world of kinetics. So don't forget to be taking your notes on a half sheet so that I can glue them in when we get a chance to get back together, or I'll make a Dropbox during this time while we're separated. I do hope we can get back together and do some of our activities, at least a week or two or something. So we'll see how long this goes on. All right, so kinetics, let's review what we've learned in chapter 13. As review, we learned that a reaction had to meet certain requirements to occur. And so if you remember, we talked a lot about the enthalpy world and then the entropy world. It gets a little confusing, but we try to keep that straight, and then how both of those kind of work together in the when you're talking about the whole system and the idea of Gibbs free energy. And so when we look at enthalpy, which would be the change in the energy of the substance, and then the entropy, the change in the, like we said in a more simplistic way, the order of the system. So those two particular things, what we call the thermodynamic criteria. So there's a certain criteria that has to be met in order for the reactions to occur and to be in line with the law of thermodynamics, the second law. So when we're looking at the thermodynamic criteria, thermo meaning the energy side, the heat, the transfer of energy from one thing to another. And so that is very important because there is certain rules to all of this fitting and the way that chemical reactions take place and what happens during them. But there's other criteria to consider. And so they give us an example in our book, and they say, okay, what about if you have hydrogen peroxide here, the H2O2, and you want it to decompose into H2O and to oxygen? And so when you look at this reaction, if you calculate it and all that with the Gibbs free energy, you'll get negative 190 kilojoules per mole. And so if you remember when we talk about Gibbs free energy, that this is going to be an indicator of a spontaneous reaction, that meaning it can occur, right? And this this little circle represents that it's at standard temperatures, room temperature, normal atmospheric pressure. And so when you see that data, you say, okay, well, then that means that hydrogen peroxide at room temperature, normal conditions, should be, decomposing, should be going through this. And if that was the case, if you're looking at constantly staring at hydrogen peroxide, you should see all these bubbles because, it should be going through its decomposition because this fits the rules for the thermodynamic criteria. But here's the thing, it is able to go through this decomposition, but there's this extra criteria to consider, and that criteria is all related to the kinetics, and that's related to what we call the reaction rate. So the rate of change of a product in a chemical reaction. So basically what it's saying is that chemical reactions, even if they do fit the thermodynamic criteria, that doesn't mean that it's going to be instantly super fast. It may be a slower reaction, it may be a faster reaction, and so you have to figure that out, the reaction rate. And so as putting this term into a formula, they give us this formula. Now, sometimes this is confusing because this formula isn't necessarily what we're calculating right now. This is just reiterating what they're saying here. And later when we start calculating using the rate equation, this sometimes throws people off. And so I don't know how productive it is, but I guess necessary to learn. So in this, they're saying, okay, the rate, the R, is equal to the change in the concentration of the product. So anytime you see the square brackets in chemistry, that means concentration. So the change in the concentration of the products divided by the time it took. And this is equal to, in a negative sense, the change in the concentration of the reactants divided by the time. Now this little negative thing might throw you off at first because it just looks like a strange equation here, but again, this is stating what a reaction rate really is, but it does sort of make sense, and from this I'll hop down to here. Well, before I do that, I'll just say, I'll explain that in a second, but the unit, when we're talking about reaction rates, the units will be molarity, because anytime we're talking about that concentration, we're talking about a molar concentration, so a molarity per second, because molarity, this is your concentration per time. So concentration per time. So molarity, big M, and then the slash and the little s for second. Okay, and so that will be your unit for the rate of a chemical reaction. So if you happen to state something that the rate at which the chemical reaction took place, you'll be using this particular unit. Now, going back to this original equation here, what it's basically saying is, okay, as the chemical reaction goes on, what's happening? Well, the products, what are they? Well, it's as the reaction is going on, the products, the concentration, I just did brackets as right out of the concentration will increase, right? Which makes sense because as you're doing a chemical reaction, you have your reactants and then it creates your products. And so in the end, your product are being made, and so your concentration increases. And when it comes to the reactants, those two things that you're putting together, the concentration is used up because you put them together and it forms the products. And so therefore being used up, it decreases, the concentration decreases. So that's where that negative sign comes in to the symbol here to balance everything out, and us understanding that this obviously increases, but when it comes to being equal to what happens here, what happens over here is the reactants end up decreasing. And so this is just balancing that side of formulating that idea of the reaction rate. Okay, so don't spend too much time getting too hyped up in this one because we'll be looking at something different when we're doing our calculations, but just so you understand that point. So as a review, it's not just the thermodynamic criteria. There's also going to be the reaction rate, figuring out what is it going to take, and if it's really a slow reaction, could I give it something that would help speed it up, something that wouldn't change the actual reaction itself. It wouldn't mess around with who bonded with who, but it could speed it up. Or if the reaction was so fast, could I give it something to slow it down without actually changing the reaction itself? We'll see later in the world of what we call the catalyst. Okay, so that's what it's introducing us to. Meeting that thermodynamic criteria, yes, you can happen. Oh, okay, but why aren't you just bubbling and bubbling and bubbling? Well, because there's other things that go along with this chemical reaction world. And we will take a look at that reaction rate. And when we do figure out reaction rates, we will use this unit, molarity per second. And that's because molarity is a concentration and time is obviously a unit of time that we got to use both of those. All right, so when we are looking, like I just said, when we are looking, let me make sure that you can see this here. Might have made that too bumpity. You see that there? All right, so when we're looking at these things, just like I said, we have to determine what factors affect the rate of a chemical reaction. Like I said, if it's slow, is there any way to just speed it up? If it's fast, is there any way to slow it down? And so we have to understand this whole world of the reaction rates, because when we're working with these experiments or these chemical reactions, certain things can be done as a basis, and then we'll look even more to things that can be added. So as a base, most of the time, now in our book, they'll give us a little experiment. Hopefully it's one we can do when we get back. So I left a page for some pictures just in case. But they give us an experiment. They have you trying to, do this simple chemical reaction, and I think with an antacid tablet and different things. And so what they do is they have you set it up to where one of the test tubes is actually taking the antacid, and instead of just keeping it in its big tablet form, you crush it and you make it powdered, which we've done that before, so we understand what happens. The more broken down you make it, then the reaction usually is able to happen faster because it has been broken down and has more surface area for the reaction to take place. Temperature, we've done ones where you change the temperature and it will increase the reaction rate. And then concentration, sometimes the concentration increase, not always, but sometimes when you increase the concentration, you get a faster reaction. And so why is that? So they have us do these experiments just to kind of introduce us to the topic. And this is why. It's because when you look at the chemical reaction, what's really happening here? To react, for the chemicals to actually react, chemicals must collide with one another so that their electrons can be either transferred or rearranged. And we understand that. That's why when you have baking soda and vinegar, and we do that baking soda and vinegar one with the balloon, the vinegar is fine by itself and the baking soda is fine by itself because they're not touching. There's no collisions among the atoms of each substance. But the moment you let them touch, then the atoms begin colliding, and there is a rearrangement of the actual atoms that make up the substance. And so in the end, instead of having the vinegar and the baking soda, you end up having the carbon dioxide that forms in the balloon, the sodium acetate at the bottom, you have the water in the container, because of that colliding. So they actually have to be able to collide and touch each other. So it makes sense when it comes to the powdered side of things. So if I take a substance and I have it in a big chunk, it can only react with the outside of the chunk, as it'll slowly, eventually, it'll react with everything in that process as it breaks down each part. But if I powder, if I put it in the bowls that we have where we chop things up, I'm losing my thought of what they're called, but the crush bowls. And when we put it in the crush bowls, then it breaks it down to the smaller pieces, and then it has the ability to do a lot more colliding because then it can touch more, right? Another thing would be the higher temperature. So when the temperature increases, the chemical reaction, higher temperature increases chemical reaction because the reactant molecules move faster, increasing the chance for collision. That makes perfect sense. We know what happens when you add energy to a system, and then the molecules they take on more of that energy, more vibration, more moving around faster. And so then you're going to increase your collisions. So would that increase chemical reactions? Yes, because the whole point of chemical reaction is you got to have them colliding so they can transfer or rearrange. All right, and then the next one is with concentration. So you increase the concentration, it makes sense that most of the time more molecules can collide. So if I have a lot of something like vinegar or whatever versus a small amount, then I'm going to have more substance to react with the baking soda. And so, but sometimes if you decrease the concentration, and so that means, now when I'm saying this, I don't mean like more in the sense like a cup of vinegar versus a cup and a half, which is terrible science. We don't use cups, but you understand what I'm saying. No, I'm talking about how much is actually in the solution. So like the hydrogen peroxide we just talked about, is it a 3% hydrogen peroxide? Is it a 30% hydrogen peroxide? Well, that's a big difference. And if you use a hydrogen peroxide in an experiment and you use a 3% versus a 30% or something like that, or 35%, you're going to have a different reaction going on. So increasing the concentration, not the amount in the container, but how pretty much packed it is inside the solution that has been made. And so more molecules to collide, you decrease the concentration, fewer molecules to collide. Now there will be some that will not follow, some reactions that will not follow this to a T. And so specifically in this concentration one, I know we have one today that doesn't follow this rate, that it doesn't matter whether you increase or decrease the concentration, it didn't change the reaction. But in general, those three things are the starting point of creating the reaction to be sped up or whatever, or decreased if you want it to decrease. Okay, so when we're looking at this rate and how we can make it faster, slower, or what the rate is for its reaction, we have to determine the rate of a reaction at any time during the reaction. And so when we're looking at a reaction, we have to figure out how could we calculate, like, what is the rate, like, at any point in the reaction, how would we figure that out? And so this is going to be the equation that we actually use for our calculation. So this is why I don't want to get confused with the first one that was just restating the definition there with the reaction rate or the explanation. All right, so let's look at this before we start to try to piece it together. First of all, R is going to be rate. K is going to be the rate constant. Now the rate constant and the exponents are going to be determined upon each substance, each reactant, and it's only going to be determined experimentally, and I'm going to show you that in a minute, or explain that in a minute. But for now, just so we don't forget, so the K is going to be a constant, the rate constant per the reactants that you're going to be working with. And then A is going to be the concentration of reactant A. So in a chemical reaction, my first reactant I'm putting together versus my second reactant I'm putting together. So the B would be the concentration of the reactant B. And then these little exponents, and remember, concentration is my brackets here. These little X components here are exponents, I'm sorry, for the concentration of the reactants. And I'm going to explain what that means on the next page, okay? But just so you have that particular formula, and we'll be using that to do our calculations to try to figure out these rates of reaction. All right, so the next page is going to be our first problem here, and it's going to help us understand how we figure out the rate of these equations. Now, when it comes to this kind of stuff, the last few videos, I've kind of left it for you to do and then just said to look in the book. But I'm going to actually do these so we can keep track of how you analyze the chart and figure it all out. And then you can, of course, you'll have some in your study guide that you have to work through anyway on your own. So that should be enough practice for you, hopefully. Doing the study guide one. All right, so when we look at the rate equation, which is the one that I just told you right here, which is R is equal to the constant, then you have your reactant number 1, reactant number 2 in concentration, and then the exponents there. So when it comes to figuring out each one of the substances, each one of the reactants and the reactions will have a different unique K and a unique X and a unique Y. Now, when we're determining those, like the book said, you kind of need certain equipment to do those. Those are the ones that can only be determined through doing experimenting. Like you have to experiment with the reactions, and you have to put the two things together and watch the time, the increase of or the different concentrations you use, and then if it increases the rate. So there's a lot to it, and it says, you know, basically at this level with high school, we're not going to have time to go into making the chart, but they're saying, okay, how about if we say someone else already did these experiments, figured out the chart, which is the data to those experiments, and then we use the chart to figure out the calculations, okay? So that's basically what's going to be happening here. So I went ahead and copied the chart for each one of these so that I just wouldn't have to handwrite them all out. And then that way they would be right there. But these charts are also in your book underneath each question. But I want you to try to do them with me without actually looking at the answer and see if it's making sense. So if you can just do this using the calculations, just using my chart. If not, feel free to open up to your book. This particular one is on page 500. Okay, if this chart is hard for you to see. Okay, so a chemist, and again, another note sheet here so I can see you practicing calculations. A chemist runs an experiment designed to determine the rate equation for the following reaction. So we're going to take a look at the rate of this reaction. So I have 2 ICLs plus H2, and it will produce I2 plus 2 HCl, hydrochloric acid. So when my formula here, this is going to be the information that was already created for us doing experimenting with this particular reaction. So they had trial number 1, that means they reacted this at a certain amount of concentration, and trial number 2, and then they did it with trial number 3, and then they recorded the data of what they were seeing. Now how this fits is we take this data from the experimenting as if we would have already done it, and that will help us figure out what goes where when it comes to the K, the X, and the Y, which are the harder ones to piece together. All right, so we take this rate equation first and get in the stuff that we know, okay? So we don't at this point know the rate because that's what we're going for, right? So what we have to figure out first then is the A and B. That's easy because we know the first reactant, the second reactant. So your first reactant is going to be the ICL. I'm going to stand up here a little bit. Hopefully I can see that there. Okay, the ICL. And then let me bracket that in. And then I have the B is the H2, my second reactant. So here's my first reactant, my second reactant. So that's going to be H2. Okay, all right, so I had those two things from my my equation up here, or my formula for this particular chemical reaction. Now, what do I need to do? Well, I've got to find the K, I've got to find the X, I've got to find the Y. So where do I start? So basically, when I'm starting to look at this, I have to remember that each time a trial takes place, there's going to be an initial concentration of my first reactant. So my first reactant, I got 0.25, right, of that guy. And then of the H2, I've got 0.25. So, and then when this happened, I had a reaction rate here, 0.0102. And so, okay, but then in the next trial, I keep my reaction of this guy the same. But what do I do here? This one gets changed. So when this gets changed, now if there is any change in this, I know it's only due to the change in this guy because this one never changed. So this is going to help me figure out my particular X or Y. Now, which one would it be? Because would it be my X or would it be my Y? So the goal is to figure out that whichever one you start with doesn't really matter, but the goal is to figure out which one your Y and your X are linked to. So what is my Y? My Y is part of this H2 guy. So if I'm figuring out his influence, like what he has done in the chemical reaction in the sense of increasing this, because this guy is staying the same. So because he's staying the same, then I don't have, and let me just highlight this, I don't have to say that he's done anything in this situation when the new change takes place in the rate. But I can definitely say that this guy has, because the reaction has changed, or the concentration has changed, and so therefore also this changes. So this change relates to him. So what is him? He is the H. So H is the B right here, right? And so this is going to be affecting my Y exponent. So my Y exponent, how does that work? Well, if I look at it, okay, he originally was 0.25, and in the next experiment he doubled. So it's 2 times the amount. And then when I look at the rate, what do I also see? It also doubled the rate. So if I look at this and I say, okay, this particular guy, and I'll just write it on here, hopefully not to get confusing, but he doubled his concentration, which also therefore doubled his reaction rate. And so if I look at both of those and I say, okay, so it's kind of a 2 over 2. And what's 2 over 2? When we turn that into an exponent, it's only going to be the number 1, right? So my Y now is going to be simply the number 1. Now, when you have the number 1 here, you don't really have to write it. It's kind of already known. So I really can, I guess I'll move this down so we can keep track of this. At this point, I still have X, so still need to know X, but I know Y is 1. I'm still going to write it just so we keep track of that. So I figured out that one there, okay? But then I want to figure out my X. So I have to look in the same situation. I got to figure out what has ICL? Has ICL contributed to any change here? So what would I have to look at? If I'm trying to look at what ICL does, I got to figure out which ones did H stay the same. So because if H stays the same, then he's not affecting it at all. And so if I look at that, let me just use a different color here. If I look at H staying the same at this point, H is staying the same between trial number 2 and number 3. So if he stays the same and there's actually a change in the rate, then it can only be because of ICL. So ICL did it this time. And so when ICL, the concentration of ICL, then that helps me figure out my X for ICL. And so when I look at this, when H is staying the same there from between 2 to 3, and I still have a change over here, then any change in rate between the 2 and 3 is got to be because of this guy. So what happened? So I look at this, and in the concentration is doubled, so from 2.5 to 50, so this was doubled, and the rate doubled as well. If you look over here, this also doubled. So this from 25 to 5.8, so that doubled that, and in the end, my result also doubled this, because look, it was 0.0204. Kind of hard to see on this one, but then now the rate was 0.0408, and so it doubled that one. So again, now I have a doubling of a doubling, just like I had double on that one too. So this also makes my X, and I'm just put my X one over here, it would be the ratio there, 2 to 2 would equal 1 in my, fraction side of things. And so I'd have this as a 1. So now I'm on to R is equal to, in brackets, ICL 1, which I wouldn't really have to write, but I'm going to do it just so we keep track of it, because if the number wasn't 1, sometimes it isn't 1. Sometimes it instead of doubling it, sometimes it quadruples it, you never know. So you have to figure that out by your experimenting, and you got to keep that straight. So then now I have those particular things. Oops, you know what I missed on both of these? The only thing that I'm missing now is the constant. So let me rewrite that because I left out the K there. So I figured out those two, and so I got that one first. I did that guy first, then I figured out that guy, and then now I got to figure out the constant. Now when it comes to the constant, this constant is going to be across all 3 trials. It doesn't matter which one you choose. You're basically going to use the information from any trial because there's that pattern there. So to calculate it, you can choose any of the 3 trials, and you just put the data into the equation, and the only unknown in the equation will be the K, so we'll get that to one side to solve for it. So I can say, okay, if I want to solve for K, then first I'm going to get it into the equation. So I have the R still, and then I'm going to have, oh, I'm sorry, I already have my R. Yeah, so I have a rate, so I can take one of these rates. Let's just do the top one. That's what the book does, is just uses the top category. So my rate over here is 0.0102. And then, oh, I better use units. Stop being a bad scientist, Miss Jody. All right, so I got my big M per little s. Okay, and then I have my my K, because I'm still trying to solve for that. That's my next guy right there. And then I have multiplied by what? My ICL, my first concentration, because that means brackets. So my first concentration was 0.25, and I don't really have to have any exponent because it's really just 1. But if there would be an exponent, I'd have to put it there. And I'd have to bracket that in, but 0.25, and then my next one would be also 0.25, and that would still be in a molar solution. So then I'm going to have to get K by itself, right? So that means I would have to take this and this and divide it by itself to get K off by itself, and I'd also have to do it on this side. So we'd have to make sure, oh, look at me writing a little m. Terrible, terrible. That's molality. Let's just mess up everything. Big M multiplied by 0.25, big M, and that should equal my K that I'm looking for, right? Because now this crossed that out. So now when I take this, then all I have to do is multiply these two, and when I multiply them, I'm going to get, on the bottom here, I'm going to get 0.0625. And then one of the m's will cross out with one of the m's. So I'll still have one m in the end. So I got to remember there's still going to be one m that still has to be in my ending. And then there's also going to be one s on. Now you do have to note this. Maybe I should write it like this. You know how you do the molar per second? Sometimes it's easier when you have to take that whole calculation and put it on top of the equation here, to keep them like this, so that if something crosses out, like this m crosses out with this m, I remember that this s is not on the top of a equation. It's still on the bottom, as is this one's a bottom one, because see that line there? So in the end, it ends up being, you know, m, big M times s as my ending once I finish this all out. Okay, so then I take this answer right here that I had from these two, and I divide it into this, which is right here. And when I do that, I end up getting 0.1632, and I got to take my big M times, or multiplied by seconds, because it's still in the bottom here. Okay, so I have that. And then when I have that, I now have my K. Okay, now I do need to note, sometimes because this is still in a fraction form, there still was nothing up here, so I would still put 1. Okay, so I have 0.16, and you would put this into significant figures with your moles. So 2 significant figures, so 0.161 m, big M, sorry, times S. Okay, so that would give me the K. And so in the end, I would have my rate, which I would say would kind of be the rate equation for this particular formula here. And it would be written, it shows you in the book that you would go R is equal to 0.16, and then you'd put the 1 over big M dot S, and then you'd put into brackets there the things, the reactants in their concentration. So ICl, L as in chloride, and multiplied by the H2. Okay, so that would be your particular rate. So you could take this rate and put it into to predict the rate of the chemical reaction for any concentration of this. So you could use this, and then any concentration that you had, you could figure this out. Okay, all right, so let's try one more. I left this page so in case we could do the experiment, I can get a picture here. And so with this, we have a chemist studies the following reaction. So we have 2 NO in a gas form, and then we have Cl2 in a gas, and we have 2 NaCl in a gas form. So I'm going to do the same thing that I did before. All I have to do is try to figure out the start using the rate equation. So I'm going to put it into its equation, like from the start. So if we just write that out, what does it look like? It's always R is equal to the K, and then that's the constant, and then you do A in brackets with your first exponent, and then you do B in brackets and with your next. Okay, so then you figure out what's your A. My A will be my NO, right? So I will get my A in there, which will be NO in brackets, and then I will get my B in there, which will be Cl right here. So I got Cl and NO, my Cl in brackets. I'm sorry, Cl2. Don't forget if it has a subscript. Okay, and then now we have to find everything else. So we want to find the K, the X, and the Y. So we figure out whichever one we want to start with. Doesn't really matter. But let's say, let's find 2 that have the unchanged in them. Okay, so let's say if we start with the Cl. So if I look at the Cl, which will be getting the Y there, let's see, there's these 2 times when the Cl, the concentration stayed the same. And so if there was a change in the rate, so between this trial and this trial, there was a change in the rate. And when you look at that, the change in the rate of the Cl, it is, let's see, I'd have to use my calculator here. what is that change in there? Is that 3 times the rate here from this? So if this stays the same, who's doing the, I should do this, who's changing it in this one? It's this guy. These two stayed the same, and I should note this too. So when the concentration of this stayed the same, this concentration changed. So therefore, the new change is because the NO2. So I guess I'm starting on this side because I got the NO2. What am I thinking? So the NO2 is making the difference there. So when the NO2, what happens here is is that 4 times that? 0.019, 36. Okay, so that is 4 times, the change is 4 times the first rate, which would be our starter point, right? So if it's 4 times the rate for my NO2, then what would that be? So I'm going to put it over here just so I can remember. So this went from 50 to a 0.50 to 1.00, which doubled it. So it went double the amount in your concentration, but the rate from here to here actually is 4 times the amount. Okay, so if it doubles this, then we have 4 times the amount with only a doubled concentration. So what would my answer be for my first one, my NO, which will be my X? So that would be 2 into 4, so my X would equal 2, okay? So that's my first one. So now I have NO2, and then I'd have to figure out the X side of things. What type of difference does a change in the concentration to Cl2 do? Okay, well then I'd have to look and say, okay, well when does the NO stay the same? So that we know if it stays the same that it's the Cl doing all the nonsense of changing it. So right here, the NO2, or not, the NO stays the same here in these between 2 and 3. So therefore, this is the one who's doing the changing. So therefore, the new change in the matter is going to be done because of the Cl2 changing its concentration. So what will that end up being? Well, right there we can see this guy stays the same, so he's out of the picture. So it means from 0.50 to 1, that doubled it. So here it was doubled, but how much did it change the rate of this particular reaction? And let me see, 76. So this only doubles it. So it only doubles this. So he doubles the concentration, but it only doubles the rate. So his influence on the situation is really only 2 to 2. So you know, anytime we get a 2 to 2, then what does that really equal? It equals 1. And so in the end, we don't really have to write the number 1 here, but I'm doing this just so we keep track of we figured out our exponents. And then the last thing we have to figure out is the K. What's the K gonna be, the constant? Well, I'm gonna have to go ahead and just put a rate in and create all of the spots filled so that I could figure out the K. So if I put a rate in, and I would take my first, I'll just start with my first, I would put 0.019, that's the first rate. Instantaneous reaction rate, and I don't want to forget this, big M over little s. And so then I would say my K, because that's what I'm looking for. Put the 0 this way. I'm looking for my K, my constant, my rate constant, and then I could easily put in my concentration, my NO2. So what's my concentration in this first experiment of NO? It's 0.5, but now I know that I have an X there, so I have to remember that. So in my first experiment, 0.5 M, which is the molarity, I have to put it in parentheses because now I have a new exponent that goes with this. And I got to remember that I figured out. And then my CL is pretty the same, 0.50 in my second one here, because I'm using this example as finding my K. And then that would be big M. Okay. Now the only reason I had to put this in so I can remember that I got to use that exponent there to multiply these by each other. So then I would do this first because it's in parentheses. So I'm just writing this out so if someone forgets how to do this, you really multiply them by themselves, which gives you 2 m's too, and that's important to note. So 0.50 times 0.50 would equal 0.25, but then you got 2 m's, so you have to make sure that is indicated with a square of the m's. Okay, then when you have that, you still have to multiply. That was just getting this one done, squaring that, but you still have to multiply it by this guy. So you take 0.25, multiply by 0.50 m, and then we have what? 0.25. Oh, well, before I do that, I want to get k away from me so that I can move it over here. So this is, I just did this one to get that there, and this one brought down here. Now, since they are both by k on this side, and I really need to get them over here to get k by itself, I then now want to move them over to get k by itself. So in order to do that, I would have to sit there and I would have to, you know, divide them by themselves and cross them out over here, and then put them over here, which would equal 25m2 multiplied by 0.50 m. Okay, so then I would do that, and then when I would work on the bottom of my equation, I would multiply these two, and and then divide up into this. In the process of doing that, I would be able to cross out 2 of my m's. Actually, I'll do that one and this one. So it's gonna still leave me with an m2. I gotta remember that m2 came from doubling it here. So I will have to do that. So I'll end up having an m2 left, and I'll end up having an s on the bottom left. So both of these will be on the bottom. I can't forget that's on the bottom of that one, that's on the bottom of this one. So when I multiply these and then divide this by what was multiplied, then my answer becomes 0.15, and then I have to have a, since there's nothing on the top, I have to have a 1, and on the bottom I'd have m squared multiplied by s. Okay, so that would be my calculations of finding every one of those particular components for the whole equation. And then in the end, I would write it like this. R is equal to 0.15 with 1 m molarity squared there times the second there, and then I would put in parentheses NO, these are the reactants squared, and then Cl in concentration, Cl2, I'm sorry. So this would be my rate. So we have to keep an eye as we're going through and finding each one of these, the K, the X, and the Y, and keep track of who and what and where. Now there's one more, but I am gonna lose my video here because my phone is about to die. So I will leave you to do this one by yourself. And then the answer to this one, let me see where this one particular one is. And this one's important because in the end, you'll realize that the concentration of the OH negative, the hydroxide, will not change the reaction. And so this is an important one to note because it actually goes against what we were just talking about, how normally the concentration will change it, but this one particularly won't. But you still do it exactly the same way, okay? And this is on page 504 and 506, but try to do it by yourself first. Put that rate equation in there, find your A, find your B, find your X, your Y, your K, and then try to get your final answer, and then look into the book. Okay? All right, so I hope that's helpful. We still have another second part to this chapter, but that gets us started, and I'll see you next time.